parameters. And then a few lectures ago, we showed that, okay, from here you can come up with a small signal model. That if, let's say, VBE changes by a small amount, but the diode that you had over there in that hybrid pi model, like what we did for the diode circuits, is represented as a resistor in the small signal model. Your current source remains the current source, the control current source you have over there, but now it's linearly proportional to whatever voltage drop you have across that resistor that is resembling your diode. We call the resistor R pi. The voltage across it is V pi, so this is RBE and VBE, but lowercase, right? Small signal. And GMV pi is the current. Now the nice thing about the model on the right side is that right away you see everything is linear. So that was the whole point of small signal analysis, right? I'm linearizing my nonlinear circuit. I go and do my large signal analysis first, figure out the bias point and everything else that I need to know about, let's say, ICs and DCEs and everything else. If my device is in an active region, it has to be an active region. If it is an active region, then I can go and linearize my circuit and look at what a small signal does to my circuit. And then to calculate all the parameters that I need to. The small signal parameters we needed to have in order to go from that model to this is, first one is transconductance, GM, which is the ratio of your DC current. So you need to do the bias analysis first. DC current, DC collector current to VT, 25 millivolts or so. And R pi that you use over there is just beta over GM. Okay? So with this, we had a small signal model for NPN transistors. We didn't talk about the small signal model for PNP. That's what we're going to spend the next 5 minutes. So this is your PNP device. IE goes in, IC comes out, IP comes out. From here,
No. Test my patience.
we can have the same model that we had for the NPN transistor. This was the large signal model, we've seen this before. Now the question is that if I want to go and come up with a small signal model for a BJT, I already have an idea how it should look like. So this is the current source, and I'm replacing that resistor with a diode. So this is my R pi again, and this is GMV pi, right? Those derivatives and all those things are the same if you have an IPN or PNP. So it's GMV pi. All I need to figure out is what is the direction for the current source, up or down, and what is the polarity for the voltage source I want to use. So this is my emitter, base, collector, and we want to see what happens, right? So let's take for a moment. For your BJT as shown here, let me just draw a simplified version so that it's easier to analyze. So I've set some VB here that is establishing some IC in this terminal. If VB goes up, right? If the voltage here goes up, what happens to IC? If VB goes up. What happens to VEB? Because slowly. You have some VEB, now you have less. So VEB will become less. What happens to IC?
Goes down.
IC goes down, right? So if VB goes up, and I can see that in this model here as well, IC goes down. IC is going this way, goes down. What does it mean? What is the small signal component direction? If IC, the original IC, large signal, was going out, now it has been reduced. What does it mean? The small signal is adding in this direction or this direction? The opposite direction, right? So your small signal goes this way. So this is the direction for your current source. If VB goes up. And if VB goes up, VEB is negative, VBE is positive. So if I choose this to be my VBE, then I can keep it as for V pi as this. So V pi is that, VBE is now positive, and GMV pi is the amount of current that's going to be subtracted from my output, my original collector current. Well, look at that. This is exactly the same as an NPN. Right? These two are exactly the same. So once you're past your DC analysis, both transistors are modeled with the same thing. Just calculate your GM and R pi, and then they're both look like, they're going to look like this in your AC circuit. No, I'm going to flip this from now on. Whenever I'm presenting let's say analyzing an AC circuit with the PNP, I flip it up and down so it looks exactly like that. So from an AC circuit, from a small signal circuit, you can't tell if the device is NPN or PNP. They behave the same way. But the reason they behave the same way is that to drive that model, we played with VB a bit. We said VB goes up, then VBE goes up, then IC increases, and that's why we have those directions. Do the same thing here. If VB goes up, the opposite things happen. IC goes down. So IC goes down means the current goes backwards. And if VBE chooses to do like that, then your models are the same. Okay, so that's for PNP, and it's really, that's all about it. Now the exciting part. This is what we've been waiting for. I don't know what you have to do. BJT amplifiers. So we want to make amplifiers. I'd say 80 to 90% of problems in analog circuit design, whatever they are, they involve an amplifier. Why? Because, well, amplifiers we already have, right? You need them to drive a speaker or a motor or whatever that you have as a load, as an actuator. Before that, you need an amplifier. If you have a small signal source, like an antenna, a small sensor, you need an amplifier to make that signal at least measurable for your digital circuit. If you have an A to D, at the input stage of any A to D, there is an amplifier. That amplifier isolates your A to D from whatever that is happening behind it. It takes a sample of your input analog voltage, gives it to your A to D. Now you have time to do the analog to digital conversion. A D to A, digital to analog converter, has an amplifier at the output. Once you have these bits converted into voltages, well, you need that voltage to be used on. There is an amplifier right there. If you want to make a filter, filters are usually passive devices if you use them in the most basic form. But a passive circuit, the problem with a passive circuit is that your signal becomes weaker and weaker as it goes through it. So usually a filter also has an embedded amplifier in it. You can have active or passive filters, both of them are doable, but in many cases you use active filters. If you have a mixer is a circuit that multiplies two signals by each other. it's an amplifier that you use it in a nonlinear way. If you have an oscillator is a circuit that produces a periodic waveform for you, a sine wave or a square wave or whatever. That oscillator is usually an amplifier with a positive feedback around it. Almost any circuit you look at in analog electronics, and especially linear analog electronics, has a tie to an amplifier. So if I want to design an amplifier, a whole bunch of problems to consider. Obviously, gain is one. Well, let me just maybe pause for a second. What do I call an amplifier? An amplifier is a circuit that sits between a source and a load. Okay, isolates the two from each other. And most of the time, deliver more power to the load than is available from your source. Right? So your source may be a 1 nanowatt signal or 1 picowatt signal that is coming from your antenna. And the load is a speaker that you're driving into, let's say watts. So 10 to the 12 orders of magnitude, 12 orders of magnitude increasing power, right? So usually, the amplifier is a circuit sitting between the source and the load, and usually, I would say usually, this is 99.99% of the time, you deliver more power to the load than what is available from your source. Gain is the ratio, well, you can define it in different ways. In RF, for example, RF communications, we define it as the power delivered to the load divided by the power derived from the source. So it's defined based on power, depending on the amplifier you use. So this microphone is probably a capacitive microphone. The output signal, again, depending on how you use it, can be a voltage or a current. If it is a voltage, I need a voltage amplifier after that. If it is a current, I need a current amplifier after that, right? So the input can be a voltage or current or power. The output, same thing, can be voltage or current or power. So gain is defined based on what topology of amplifier you're using. The other issue is, let me go through a bunch of them. Bandwidth, or let's say bandwidth is one. If I want to amplify my voice, most of its energy is between the first 10 kilohertz of bandwidth, right? An RF signal has energy in megahertz and hundreds of megahertz. And the thermocouple that is measuring the temperature in this room is very close to DC. High frequency response and low frequency response. So bandwidth is one thing, but what is the edge? What is the corner? Before that you basically may not see a signal, low frequency may not go all the way to zero. And high frequency, I guess most of you kind of know that cannot go to infinity. There is a limit on how high a frequency your device can operate at. There is a limit for low frequencies in some cases too. Linearity is a big issue. Maybe right after the gain. For an amplifier, in majority of the cases, you want it to be perfectly linear. You want whatever parameter at the output you're measuring, let's say PO, to be some constant times PO. VO to be some constant times II. But you want it to be linear. And so that linearity is very important for a variety of reasons. If you're dealing with RF systems, non-linearity means that you're going to produce spurious signals and RCMP is going to come and look after you. If you're listening to some audio signal, non-linearity means distortion. You don't like it. So linearity is very, very important when you're making amplifiers. Available power at the output. So I can make an amplifier with a gain of 100, but I cannot use the same amplifier to amplify the signal from, let's say here, to drive a big speaker or a small speaker. They require different amounts of power. I need to use different types of amplifiers for the same gain, but the load is demanding different types of drivers. what else? Let me see. Efficiency. And this is more and more important nowadays. Most of your electronic devices are running off batteries, right? Your amplifier cannot be 5% efficient. It has to be very, very efficient. And what is efficiency? Efficiency is the power delivered to the load versus the power you use. The power you use is usually DC power. It's usually wasted through your biasing network and everything else. The power delivered to the load is some sort of a periodic signal, right? So you want this to be as close as possible to 1. You don't want to waste a lot of power on biasing. That's not giving you really louder signal, right? Supply requirements. So if your power supply is only 1.5 volts, right away most of the MOSFETs are ruled out, the discrete MOSFETs, because their threshold voltages is larger than that. So the topology you use is going to kind of depend. Supply, let's say, requirement or availability, things like that, right? And then one more thing is noise. This is very important in a lot of higher-end amplifiers. Day-to-day stuff, you usually can find something off the shelf to meet the requirements. But for high-end stuff, noise is basically going to, in many cases, it can be more important than the rest, right? So these are all the parameters that we need to design for any amplifier. And it's always a trade-off. You go and improve the efficiency, right away you most likely destroy your noise performance. You fix this, you destroy your linearity. You fix that, your gain is screwed up. You fix that, your bandwidth drops, right? It's usually a trade-off between all of these. You know, it's very, very rare that we improve one thing and all of the rest, or most of the rest improve it at the same time. The only time that it may happen is that if you sacrifice power or efficiency to gain, usually you gain in a lot of those other areas. If you consume more power, you usually have better linearity, you have better noise performance, you might have better bandwidth, right? So this is the only one that usually improves a bunch of parameters at once, but this is usually the one that you don't want to spend, right? Because you're running everything off of batteries. So, how does an amplifier look like? Well, let's look at the voltage amplifier for now. This is how we model a voltage amplifier. We assume there is a magical control voltage source inside the black box, or in this case a blue box, which has some input resistance, some output resistance, and some gain. So this some gain times V. Okay. This is the generic model for a voltage amplifier. Okay. It's as if I've taken a huge circuit and used Thevenin as a few times, the Thevenin theorem a few times on that circuit, reduced it to just these 3 components. If you're not worried about bandwidth and linearity issues, and usually you're not with linearity, your small signal circuits, remember, what are they? Just a bunch of resistors and controlled current sources. That's all your small signal circuits. You should be able to reduce them to something like this. So there is a box, it gives you all the stuff that you want. It has an input resistance, an output resistance, and a control voltage source that gives you the gain. So let's just quickly check. For an ideal voltage source, what do I like the RA to be? Sorry, voltage amplifier, not voltage source. What do I like RA and RR to be?
The same. You said something about that. That's meant.
So I give you an answer that is not right. For RF, I want both of them to be 50 ohms, but that's not the answer we want to have. Right? Well, what is ideal voltage source? So what is an ideal voltage source? An ideal voltage source is an ideal voltage amplifier. Is an amplifier that when it measures the signal, when it tries to amplify a signal, your source will not even know it. It measures that signal without, so basically the power drawn from your source is zero. Your source, it's like an oscillator, it's like a multimeter. You touch that point, measure the voltage across your source, and your amplifier will do the rest. Your source should not even notice your amplifier is there. So what should be the R in for an ideal amplifier?
First one.
You want it to be open circuit, right? If your source should not know that I'm touching it, well, I should not draw any current. I should touch it with an open circuit. Infinite input resistance. What about R out? So R out, after I do my amplification and everything else, I'm driving a load. There's a load attached here. There's a source
This is the part.
attached here,
The small part.
ES and
This is the big
RS.
part.
And there's a load attached to the other end. So at the input we took care of, right? So if your Rin is infinite, you measure all of Vs. Rs doesn't matter anymore. What about output? What is an ideal value for R out?
0.
0. I want all the voltage produced by my source to appear across the load. If the two are comparable, if R out is large, I'm wasting some of my signal across R out. What I'm measuring or what I'm hearing or what I'm feeling is what is across R in. Right? Anything across R out is inside the amplifier. I will not see it. I will not know about it. So I want to minimize that. So R out, I want it to be 0. R in, I want it to be infinite. And G, whatever the I want to set. Right? But this is the generic model for a voltage amplifier. Unfortunately, you don't get these. You don't get an infinite input resistance. You don't get the 0 output resistance. You get something less than infinite for your input, more than 0 for your output, right? So we need to always go and calculate it. Because, for example, if you have multiple amplifiers connected to each other, this is amplifier 1 connected to amplifier 2 connected to amplifier 3. And there is a load here. Let's see, there is an antenna or source, a small signal source here. The signal is pushed through a bunch of these amplifiers. They may be different, they don't have to be the same. Okay? Right away you can see that if I call this VI2, and let's just call this V out. So V out is going to be a voltage division between RO2 and RF. So RL over RO2 plus RL times, let's say, G2 VI2. Right? So that's easy. At the output, I can quickly write that. But what is VI2? VI2 is the voltage divider between the input resistance at the second stage and the output resistance at the first stage. Okay? So this is RO1, let's call it. This is RI2. And then I have the voltage division between those two. So RI2 over RO1 plus RO2 And then Vi1, in a similar fashion, is Vs times Ri1 over Ri1 plus I. So they load each other. A second amplifier that you connect after the first one loads the first one. How much? Well, it depends on the ratio of Ri2 and Ri1. So if I'm designing a chain of amplifiers, which I usually have to do, because in most cases I cannot get the job done with just one stage. I usually have to have a few stages of amplifiers. They are going to load each other. So if, let's say, Ri2 is, you can say it right away. So if Ri2 is much smaller than Ri1, let's say Ri2 is 1 over Ri1 is 1 kilo. Right? This ratio is 1 over 1,000. Well, you have to have at least a gain of 1,000 to get an overall gain of 1. You don't lose your signal. Right? And then so on and so forth. So you need to know what's going on in your circuit. You need to know how much these circuits, these amplifiers, these different stages are affecting each other. And for that reason, there is a concept called impedance at a node. That you want to know, if I look to the left, what is the resistance that I see effectively? What is the resistance that I see over there? And, or maybe if I look to the right and this is look to the left. Right? What is the resistance that I see when I look back? What is the resistance that I see when I look forward? And then I can calculate, let's say, this ratio. Right? So in general terms, if I want to have an amplifier chain, I want to make sure that the resistance I'm seeing in front of me is much bigger than the resistance that I had before me. Right? If the signal is going through that chain. But that depends. Right? But I need to know. This is called an impedance at the node. Why at a node? Well, okay, here is why we call it at a node and not at the cut set. Because usually this bottom line is ground. And it's a common ground between all amplifiers. So I cut just one line to measure resistance. In reality, I know it's a current that goes and comes back. Right? It's a cut set, it's not a node. But anyway, it's called impedance at a node. What I want to do is I want to measure the resistance or estimate the resistance. Whatever I have here, we'll see if I connect that second circuit to it. Or if I'm a load down here, I want to know what is the resistance of that amplifier, the output resistance of that amplifier that is going to connect to it. Or if I'm source here, same thing. I want to know how much is the resistance that I see. Once I figure those things out, I can create a chain like this, very easily solve my problem, right? So just go through a couple of multiplications and solve my problem. So figuring out that impedance is very important. Knowing that impedance or resistance is very important. Let's just see where is the. Let's just see how we calculate that resistance. I hinted to it. It's the Thevenin resistance, right? So once we are dealing with these amplifiers and we're dealing with linear amplifiers, we're using the small signal model. Your circuits are linear. From now until the rest of this course, whenever we talk about small signal and amplifiers, life is easy because everything is linear. No e to the power of this and that. Circuit is linear. So all I need to do is to find the Thevenin equivalent resistance, let's say, when I look back. Or when I look this way. That's all I need to do. Okay? So those impedance at the node or resistance at the node is that I cut my circuit from that node, both of those lines, and I attach my test source, measure how much current is coming from a test source, that's my equivalent resistance. Now I can do it for the guy on this side too. Okay?
Where's
RS is that input source. So V source, R source. Okay, so let's do this for a couple of circuits and see what we learn. Assume that I have a biased EJT, properly biased in active region. I'm asking you, what is the impedance? When I look into the base, let's just say RIB. What is the impedance when I look into the collector? I'm asking you, what are those two impedances, right? The assumption here is that the device is happily biased. I'm not showing you the bias network, all of that stuff. There is something, let's say there's an H bias network that is connected to the base to keep this device happy. We are not concerned about that. We're looking after that stage. Okay. So the question is, what are RIB and ROC? Assume the device is in active region. Whenever I say amplifier in this course, I mean the device is in active region. Right, so if I don't mention it, that's implied. Okay, if it is an active region, I have a small signal model. And I'm interested in the resistance that I see when I look here or here. Okay? So let's consider one of them for now. Let's consider RIB for now. I want to figure out what is RIB when I look into the base of the device. So for now, I'm going to go and connect the collector to ground. Because I'm not interested in that part for now. And it really doesn't matter what I have on the collector side, right? For whatever analysis I do here, it doesn't matter what I have at the collector. Why doesn't it if I have a short circuit or some resistor?
Current source?
It's behind the current source. Whatever I have here, the current here doesn't change. Right? It doesn't matter what I have. So for now, let's just ground it. It shouldn't be open, because then you have a problem with your current source. It shouldn't be open, but whatever else it is, it doesn't matter. So I attach my test source to the input of this circuit. You can use a current source or a voltage source. What I do is that I attach a test source. This is my source, 1 volt. Or I just call it Vx, and I measure Ix. Sometimes you look at the circuit and it's easier to use a current source. You attach your Ix to the input of your circuit and you measure Vx across it, right? But the idea is that if I could represent everything here as a resistor, Vx over Ix would give me that resistor value. It's the Thevenin equivalent current. Okay. So if I want to do that, help me. How do I do that? So I went from that circuit to this. Right? Any problem with going from that circuit to this small signal? No. Okay. Yeah. Look at the suggested problems, right? The chapter 5. But anyway, and actually chapter 4. Anyway, I want to solve this circuit. I want to find Ix. How do I do that? Give me an equation that helps me find Ix. Only 15 minutes and I have to teach you 3 more circuits.
What?
Oh, just 2.
That's now.
I write the KVL. To ground. Right? So that KVL says Vx is equal to well, this voltage is V pi. or I can say the current Ix is going to R pi. So Ix R pi. Then I have a current Ix coming from the left side and GMV pi from the right side. They add up at that node, go through RE plus Ix plus GMV pi. These are the two currents and RE. Okay? Alright, it looks like I have two unknowns. If Vx is known, if Vx is my source, I don't know Ix and I don't know V pi. So I need one more equation.
Does R pi equal beta over GM?
Sure. How does that help?
Just for the future.
Yep. And GM is IC over D. So I'm assuming that we've done the DC analysis, I have those values. So I'm assuming I already know R pi and GM. Okay, the biasing is taken care of.
Sounds like a cute American.
Yeah. So if I look at that circuit, V pi is Ix R pi, right? This voltage drop of V pi is current times R pi. Okay, done. I have my Ix. You know what? I'm not interested in Ix. I want RIs. You can just write it as Vx and Ix. So Vx is now equal to Ix times R pi plus 1 plus Gn Rx R pi times R. Okay? And RIB, the impedance when I look into that base, is the ratio of these two, Vx to Ix. And from that expression, it's just R pi plus 1 plus Gm R pi. Okay? So that's the impedance that I see when I look into the base. Doesn't look too pretty. But what is Gm R pi?
That's
Gm R pi is just bigger. If I multiply this by Gm, it's bigger. Okay. This is genius. I don't know what you're not to say.
Yay.
Okay. So let's use a number here for IC. Let's say IC is 1 million. If IC is 1 million and beta is 100, let's say, then GM is 40 millisiemens and R pi is 2.5 kiloohms. Okay, for those numbers you get these values. Okay. So you are connecting this as, let's say, your second amplifier stage to the previous one. And if you don't have an RE, your input resistance is just this much, R pi. Right? If RE is 0, you have just that much. The input resistance of that circuit, the next stage, is only 2.5 kiloohms. Is it large? Is it small? It's not too big. Usually for input resistances at small frequencies, I'm expecting tens of kiloohms to tens of megaohms. 2.5 kiloohms is not that attractive. Okay? So I'm hoping that I can play with my circuit such that its input resistance goes up. Well, that's easy. If I want 100K, just use a 1 kilo ohm resistor for RE. It's going to change my biasing and everything else, right? And that's part of the design. But by using a 1 kilo ohm resistor here, I get a 100 kilo ohm resistor at the input. Whatever resistor I use in a meter appears as beta times larger when I look into the base. Right? That's the nice thing about this. You know, that's part of the magic here. Because what you draw from the source is IB. What you dump across RE is IE. You dump beta times more current through this RE than what you draw from the source. To your source, it's as if you have a beta times larger resistor here than you do. But the current doesn't come from the source. The current comes from this other source that we have in your circuit, right? So this is great. If you want to play with your input resistance, please go whatever limit is. Choose whatever RE you want to get whatever input resistance that you want. Within reason, right? You don't get 1 kilo ohm out of this. Within reason. Hopefully, you're reasonable. But this is beautiful. But this is also, I think, the first rule of BJT impedances. I don't know, maybe they call it the rule of BJT impedances in your book. But anyway, when you look into the base, emitter, the equivalent resistance in the emitter circuit appears as beta times larger. And all you have is just 1 alpha you series. Right? Whatever you have in the emitter times beta plus alpha. Good. Let's look at ROC. So in this case, I'm going to connect my input to ground. I don't need your input source anymore. Here's my output. This is deleted. And the question is that how much is IX, because I want to find VX over IX, right? ROC is when I look back into the collector. So I look at this. I try to, if I'm asking for IX, I try to write an equation for IX as soon as I can. Right? Because then I can figure out what is needed, what else is needed. So in this circuit, what I can see is that IX is equal to GM V5, right? Anybody can guess? Can anybody guess what is IX? 3, 2, 1, go.
Current source? Oh man.
IX is IX, so that's
Hey, voltage pi, huh?
IX.
Yeah.
Well, let's see. Let's see what
Just say
happens.
all the
Okay, so IX is GM V5. Based on that circuit, it must be, right? Okay. So I need to find V5.
That's what I said.
How do I find V5?
That's right.
That's what's
You can write a KVL here. Doesn't really help you. In this case, I'd like to write a KCL here. At this one, right? Because I'm playing with currents. Like, I look at the current over there, there's a current source attached to this node. I should be able to write a KCL. Let's do the KCL. So let's call this VE. The voltage here. And because it's a small signal, lowercase. So I can say this current plus this current plus this current should add up to 0. Or because GMV pi is entering, I can say this current should add up to the other two. So GMV pi is equal to VE over RE plus VE over RI. Huh. I now have one other unknown, VE. What is VE? So I need one more equation, or I need to get rid of it somehow. What is VE?
That's IERE. But
That's current.
Voltage at the bottom of R fine. Voltage across R fine is V5. I connect the top of it to ground, so what is VE?
It's a negative V pi. Oh.
Right? If I call that voltage drop V pi, VE must be minus V pi. Then I'm done. I'm done.
Well, if you have ground here, and then you go, there's a voltage drop across the resistor, and then you take.
Oh, and V pi is connected to ground, so it drops it down.
Okay?
Yeah.
I just saw that.
So one equation, one unknown. What is V pi?
Yeah, it goes to. So,
Come on.
Drops it down.
So if we're an active region and we're trying to find VE, why don't we just say that VE is equal to IERE, which is going to be equal to the scalar relation with
You're going to be back
GM.
here. This is the same thing. That JCL, no, VE equals to IERE. IE is GN V pi plus V pi over R pi, you can say, times RE. Get back to here. It's the same equation.
What is ROC showing?
The resistance when I look back in the collector. This resistance. This is the chain of amplifiers. I'm cutting it from nodes. I'm looking back, right, to figure out what the impedances are the node are, right? So don't worry about what is connected after it. It's just that we're doing it before, right? So ROC is the name of the variable. Okay, so V pi, if it is satisfying this equation, it must be 0, meaning that what is GM pi? See, I should have expected that. I should have known that result without solving it. Why? Because from the beginning of the discussion on BJTs, we said collector acts as a current source. What is the output resistance of a current source? When you look at a current source, what is the resistance you measure? Infinite,
Oh.
right?
Maybe
The other
it's-
way to look at it. Over here,
Yes.
ROC, you attach your source, right, to the collector, and you're playing with the collector voltage, you want to see how much the collector current will change. It wouldn't, because you're playing with the voltage across a current source. Or, here's yet another way to look at it. The current source here is a function of some other voltage somewhere else. If you play with the voltage across it, V pi is not changing, right? So for all those reasons, you do not expect Ix to respond to changes in Vx. But you can also do the small signal analysis and actually show that it's accurate. So here is another point to remember. When you look into the collector of a BJT, you usually see an open circuit. Right? It's an infinite resistance. When you look into a collector terminal, you see an open circuit. You look into the base, you see R pi plus beta RE. What do we have for RE? Because you're good kids and you didn't let me finish, show this at home. We can do this at the beginning of the next lecture, but give it a try. RIE, if the device is in active region and I look into the emitter of this device, something magical again happens here.
I think that means it's either 0 or infinity.
I think it's 0.
It probably is.
We can prove it next lecture, but so that we have all three loops. When you look into the emitter, any resistance you have in the base circuit appears to be beta times smaller.
Mm-hmm. Okay, that makes sense.
That's great, because if I want to attach an 8 ohm load here, and that 8 ohm load is too small for whatever I have, the amplifier and everything else here, I can design an amplifier such that the output terminal is an emitter. Because then whatever I have before it is 100 times less, 200 times less. So if I have 8 ohm here, I'm getting much smaller resistors. We'll talk about that later. But anyway, show this at home. Draw the small signal model for the transistor, get the connector connected to ground, doesn't matter really. And see if I attach a test source here, how much current will it draw from my test. Okay, that's the end of the lecture for today. So for next lecture, we are going to talk about how to make amplifiers. Now we know how to calculate input and output resistances, calculating gain is the same thing, use the small signal solve it, and we're going to use this information to make amplifiers. Alright, no labs this week, no quizzes this week, no assignments this week. Do the suggested problems.